Welcome to this coding walkthrough. Today, we'll be diving into LeetCode problem number 948, titled Bag of Tokens. In this video, we'll explore the problem statement, break it down, and step through a possible solution. Let's get started. In this problem, we are tasked with maximizing a score using a bag of tokens and an initial amount of power. Each token in the bag has a specific value, and you can interact with these tokens in two ways. First, you can play a token face up to gain 1 point in your score, but this action reduces your power by the value of the token. Second, you can play a token face down to gain power equal to the token's value, but this action decreases your score by 1 point. Each token can only be used once, and you don't have to use all tokens. The objective is to determine the highest score you can achieve after performing these operations as many times as you'd like, in any order. The input to the problem consists of two elements, an array of integers called tokens, where each element represents the value of a token, and an integer called power, which is the amount of power you start with. The output is a single integer representing the maximum score you can achieve. Let's explore this through some examples to understand how the operations work and how the score is calculated. In the first example, the input consists of a single token with a value of 100 and an initial power of 50. Since your power is less than the value of the token, you cannot play it face up to gain a score. Additionally, since your initial score is 0, you cannot play the token face down to gain power. Therefore, no operations are possible, and the maximum score remains 0. Now consider a case where you have two tokens with values 100 and 200, and your initial power is 150. In this scenario, you can play the first token face up, which increases your score by 1 and reduces your power to 50. However, the second token cannot be played face up because your remaining power is less than its value, and it also cannot be played face down because you would need at least one score to perform that action, which you no longer have. As a result, the maximum score you can achieve is 1, based on the operations you were able to perform. In a slightly more complex example, suppose the tokens have values 100, 200, 300, and 400, and your initial power is 200. To maximize the score, you could first play the token with a value of 100 face up, gaining 1 score and reducing your power to 100. Next, you can play the token with a value of 200 face down, losing 1 score but increasing your power to 300. With this additional power, you can play the token with a value of 300 face up, gaining another score and reducing your power to 0. The fourth token cannot be played due to insufficient power, so the maximum score achievable is 2 after these operations. There are a few key constraints and edge cases to keep in mind when solving this problem. First, if the tokens array is empty, no operations can be performed, and the score will always be 0. Second, if all token values are greater than the initial power, you won't be able to play any tokens face up, resulting in a score of 0. Third, strategic management of score and power is critical. Sometimes, you may need to play a token face down to gain enough power to play another token face up. For example, playing tokens in the right sequence can make a significant difference. Finally, in cases where there's only one token, the score will be either 0 or 1 depending on whether the token's value is less than or equal to the initial power. On the other hand, if your power is significantly higher than all the token values, you can simply play all tokens face up to achieve the maximum possible score. To solve the bag of tokens problem, one approach we could consider is a brute force method. This involves trying every possible sequence of token operations, starting with the available power and score, and simulating all combinations. Specifically, we explore playing tokens face up, which costs power but increases the score, and playing tokens face down, which sacrifices score to gain power. This approach guarantees that we find the optimal solution since it exhaustively examines all possible outcomes. However, the downside is the sheer computational cost. With each token having 2 states, the total combinations grow exponentially, resulting in a time complexity of O(2 to the power of n, where n is the number of tokens. Additionally, the recursion depth requires O(n) space, making this approach impractical for larger inputs. To address this inefficiency, we can consider a greedy strategy. This approach focuses on 2 key principles. First, spending power on the smallest tokens to maximize the score gained for minimal cost, and second, regaining power with the largest tokens when the available score permits. By prioritizing actions that provide the greatest immediate benefit, this method significantly reduces the computational burden compared to brute force. With the greedy approach, we can break the solution into clear, manageable steps. First, we sort the tokens in ascending order, ensuring that the smallest token is readily accessible. Then, we utilize two pointers, one starting at the smallest token, referred to as left, and the other at the largest token, referred to as right. While there are tokens left to process, we follow a simple decision process. If the current power is sufficient to play the smallest token, we play it face up to gain 1 score and reduce power by the token's value, then move the left pointer forward. However, if the power is insufficient but the score is greater than 0, we play the largest token face down to regain power equal to its value, lose 1 score, and move the right pointer backward. The process halts when neither of these moves is possible. This strategy minimizes the power spent per score gained by focusing on the smallest tokens first, while using the largest tokens strategically to regain power when necessary. In terms of complexity, sorting the tokens takes O, n log n, and the two-pointer traversal is linear, making the time complexity O, n log n, overall. Since we only use the pointers and no additional data structures, the space complexity is O1, which is highly efficient. The greedy approach was chosen for its balance of efficiency and simplicity. It dynamically adjusts decisions based on the current state of power and score, ensuring that each move contributes to maximizing the outcome. Unlike the brute force method, which explores an exponential number of states, the greedy approach focuses only on the most promising actions, making it scalable for larger inputs. While brute force guarantees the optimal solution, its exponential time complexity renders it impractical except for very small inputs. The greedy strategy, on the other hand, achieves optimal results efficiently by leveraging local decisions that align with the problem's global goal. This efficiency is rooted in the problem structure, where tokens can only be played once and the power score dynamic favors localized optimization techniques. Ultimately, this approach offers the best trade-off between computational feasibility and solution quality, making it the ideal choice for solving this problem within the given constraints. The goal of this problem is to maximize your score by strategically playing tokens face-up or face-down. Playing a token face-up means you spend power equal to the token's cost and gain 1 point in your score. On the other hand, playing a token face-down allows you to gain power equal to the token's cost, but you lose 1 point from your score. Starting with an initial amount of power and score, the challenge is to determine the maximum score you can achieve by playing tokens in any valid sequence. To approach this, we begin by sorting the tokens in ascending order. This sorting step helps us efficiently decide which tokens to play face-up or face-down. Additionally, we set up two pointers, one at the start of the token list to handle the cheapest tokens, and one at the end to manage the most expensive ones. We also initialize current_score to track the score during the simulation and max_score to store the highest score achieved. With this setup, we can now simulate the gameplay to maximize the score. The simulation uses a two-pointer approach to decide the sequence of token operations. While the left pointer is less than or equal to the right pointer and there are valid moves to make, we consider two options. The first option is to play a token face-up, which is only possible if our current power is greater than or equal to the cost of the token at the left pointer. If this condition is met, we spend the token's cost in power, increase current_score by 1, and update max_score to ensure it reflects the highest score achieved so far. After this, we move the left pointer forward. The second option comes into play when we don't have enough power to play the token face-up but have a score greater than 0. In this case, we play the token at the right pointer face down, gaining power equal to the token's cost and reducing current_score by 1. We then move the right pointer backward. If neither option is valid, it means no further moves can be made, and the loop ends. Once the simulation is complete, the maximum score stored in max_score is returned as the result. The algorithm relies on a few key insights to work efficiently. First, sorting the tokens at the beginning ensures that we can prioritize cheaper tokens for face-up operations, which minimizes power expenditure. At the same time, we keep the more expensive tokens available for face-down operations, allowing us to maximize the power gained when needed. Second, the two-pointer technique provides an elegant way to manage the sequence of operations. Incrementing the left pointer corresponds to playing tokens face-up, while decrementing the right pointer corresponds to playing tokens face down. This avoids repeatedly scanning the array and keeps the simulation efficient. Finally, it's important to handle edge cases carefully. For example, if the initial power is less than the cheapest token, no face-up moves can be performed, and if the token list is empty, the maximum score is simply 0. Additionally, the algorithm must account for scenarios where only face-down moves are viable, such as when token costs are high and the initial power is low. The data structures used in this algorithm are straightforward but critical for its efficiency. The array of tokens holds the costs of the tokens, and sorting this array enables quick decision-making during the simulation. The 2 pointers, left and right, are used to keep track of the next token to play face-up and face-down, respectively. This eliminates the need for additional space or complex bookkeeping. The algorithm's time complexity is dominated by the sorting step, which takes O, n asterisk log n, where n is the number of tokens. The 2-pointer simulation itself runs in O, n, as each pointer moves at most once through the array. Thus, the overall time complexity is O, n asterisk log n. The space complexity is O, 1, since all operations are performed in place on the sorted array, requiring no additional data structures. This combination of simplicity and efficiency makes the approach well suited for the problem requirements. This Python implementation solves the bag of tokens problem using a greedy 2-pointer approach. Here's the breakdown. 1. Input and initialization. The tokens list is sorted in ascending order, ensuring the smallest token is at the leftmost position. This allows us to play the smallest token face-up to maximize score. 2 pointers, left and right, are initialized at the start and end of the sorted tokens. Additionally, score tracks the current score, and max_score keeps track of the highest score achieved. 2. Greedy strategy. The algorithm runs a loop while left equals right, processing tokens from both ends of the list. If the current power is greater than or equal to tokens, left, the smallest token is played face up. This decreases power by tokens, left, increases the score by 1, and updates max_score to the maximum of its current value and the new score. The left pointer is then increment. If power is insufficient to play the smallest token but the score is greater than 0, the largest token is played face down. This increases power by tokens, right, decreases the score by 1, and moves the right pointer leftward. If neither condition is met, i.e., no valid move is possible, the loop breaks. 3. Result. The function returns max_score, representing the maximum score achievable with the given tokens and initial power. This approach ensures that tokens are used efficiently to maximize the score. Sorting the tokens takes O, n log n, and the 2-pointer traversal operates in O, n, resulting in an overall time complexity of O, n log n. The space complexity is O, 1, as no additional data structures are used. Here, we start by importing the necessary utility classes and defining our solution class. The main method, BagOfTokensScore, takes 2 inputs, an array of tokens and an initial power. The first step is to sort the tokens in ascending order using arrays.sort. This allows us to efficiently decide which tokens to play based on their values. Next, we initialize 2 pointers, left and right, to the beginning and end of the token array respectively. We also set up 2 variables, score to track the current score and max score to keep track of the highest score achieved during the process. The while loop ensures we continue processing as long as the left pointer does not surpass the right. Inside the loop, we handle 2 possible actions. First, if the current power is greater than or equal to the token at the left pointer, we play the token face up, which increases our score. We then deduct the token's value from our power, update the max score if the new score exceeds it, and move the left pointer forward. This represents the case where we use smaller tokens to gain points. On the other hand, if we don't have enough power to play the smallest token, but we have accumulated some score, we can use that score to regain power. This is done by playing the token at the right pointer face down. We add the token's value back to our power, decrease the score by 1, and move the right pointer backward. This trade-off allows us to potentially gather enough power to play smaller tokens later. However, if neither of these conditions is met, meaning we don't have enough power to play a token and our score is 0, we simply break out of the loop, as no further moves are possible. Finally, once the loop ends, we return the max score, which represents the highest score achieved during the game. This approach ensures we maximize the score by efficiently balancing power and tokens through sorting and strategic use of the 2 pointers. In this example, we start with a single token array, 100, and an initial power of 50. The first step is to sort the tokens, which doesn't change the array since it only contains one element. We then initialize our variables, left and right pointers both at 0, score at 0, and max_score also at 0. Entering the while loop, we check if the current power is sufficient to play the smallest token face-up. Since 50 is less than 100, we cannot gain a score. Next, we check if we can regain power by playing a token face-down, but that also isn't possible because the score is still 0. With no valid moves available, the loop terminates, and we return the max_score, which remains 0. This demonstrates a scenario where no tokens can be used due to insufficient power. Now we consider an input with more tokens and a higher initial power, 100, 200, 300, 400, and 200 power. After sorting the tokens, the array remains the same. We initialize left at 0, right at 3, score at 0, and max_score at 0. In the while loop, the first condition power equals tokens, left, is true because 200 is greater than or equal to 100. This allows us to play the smallest token face-up, reducing power to 100 and increasing the score to 1. We then update max_score to the maximum of its current value in the new score, which becomes 1. Next, we increment left to 1. However, now power equals tokens, left, is false since 100 is less than 200. Instead, we check if we can regain power by playing the largest token face down. Because the score is greater than 0, we play the token at right, increasing power to 500 and reducing the score back to 0. We then decrement right to 2. Returning to the loop, the increased power now allows us to play the next smallest token face up, reducing power to 300 and increasing the score to 1. The max_score remains 1. Incrementing left to 2, we can continue by playing another token face-up. This reduces power to 0, increases the score to 2, and updates max_score to 2. Finally, as no further moves are possible, the loop ends. With no valid moves left, we return the max_score of 2, which represents the highest score achieved during the process. This example highlights the importance of balancing when to gain scores and when to regain power to maximize the final score. By strategically alternating between these two actions, we achieve the best outcome given the constraints of the tokens and initial power. To summarize, the key to solving this problem lies in sorting the tokens first. Sorting allows us to efficiently decide whether to gain a score by playing the smallest token or to regain power by playing the largest token. The left pointer helps us track the smallest available token, while the right pointer tracks the largest. The algorithm is designed to prioritize gaining scores whenever possible, only regaining power when the score is already greater than 0. The max_score variable ensures that we always retain the highest score achieved during execution. The loop terminates when neither gaining scores nor regaining power is possible, ensuring we stop once all valid moves are exhausted. This greedy approach effectively balances between gaining scores and recovering power, enabling us to maximize the score under the given constraints. To analyze the time complexity of the algorithm, we start with the sorting step. Sorting the tokens array in ascending order is the most computationally expensive operation here, taking O, n asterisk log, n, time, where n is the number of tokens. Once sorted, the algorithm uses a two-pointer approach with a left pointer starting at the beginning of the array and a right pointer at the end. The while loop runs as long as these pointers don't cross, and in each iteration, either the left pointer is increment or the right pointer is decrement. This means the maximum number of iterations is proportional to the size of the array, or O, n. Within each iteration, operations like condition checks, pointer updates, and modifications to power or score are performed in constant time, O1. Combining these steps, the sorting operation dominates, giving the overall time complexity of O, n asterisk log n. Now, let's consider the space complexity. The algorithm modifies the tokens array in place, so no additional space is needed for the input. However, the sorting operation may require auxiliary space. Specifically, if timsort is used, it can require O log n space for handling the recursion stack. Beyond that, the algorithm uses only a fixed amount of space for variables like left, right, power, score, and max_score. These do not scale with input size, so their contribution is constant, O(1). Therefore, the overall space complexity of the algorithm is O log n, driven solely by the auxiliary space required during sorting. When we compare this approach to a brute force solution, the difference is significant. A naive approach would involve trying all possible combinations of tokens to achieve the maximum score. This would mean exploring every subset of the tokens array, leading to an exponential time complexity of O(2 to the power of n. Such an approach becomes computationally infeasible for larger inputs, as the number of subsets grows exponentially with the size of the array. On the other hand, the current approach leverages sorting and a two-pointer traversal to make greedy decisions efficiently. These optimizations reduce the time complexity to O n asterisk log n, and the space complexity to O log n, making it far more practical for real-world scenarios. Finally, let's analyze the algorithm across different cases. In the best case, all tokens can be played face-up without the need to play any tokens face-down. This means only the left pointer is used, and the traversal processes the array in O n time. However, since sorting is still required, the total time complexity remains O n asterisk log n. In the average case, the algorithm alternates between playing tokens face-up and face-down, resulting in a similar O n traversal and overall O n asterisk log n time complexity. Even in the worst-case scenario, where the algorithm must play many tokens face-down due to high token costs or low initial power, the traversal still processes each token at most once. This ensures the time complexity remains O n asterisk log n. The greedy strategy is mathematically justified as it ensures tokens are played in the most optimal order, minimizing unnecessary computations. The sorting step supports this efficiency, while the space usage remains limited to the sorting process, keeping the space complexity at O log n. When solving problems like the bag of tokens, there are a few common mistakes to watch out for. First, not considering edge cases can lead to incorrect solutions. For instance, scenarios involving empty inputs, single-element arrays, or all elements being identical can reveal flaws in your logic if they're not tested. Imagine a problem where you need to maximize a score. If all the elements are negative and you haven't accounted for that, your solution might behave unpredictably. Another frequent mistake is inefficient use of resources. Brute force approaches may seem straightforward, but they can be impractical for large inputs, especially when the constraints demand optimization. Always analyze the problem's limits and consider efficient methods like greedy algorithms or dynamic programming. Finally, overcomplicating your solution is another pitfall. Adding unnecessary data structures or overthinking the problem can make your code harder to read and debug. Instead, begin with a simple approach, focusing on clarity, and then build from there if needed. Additionally, ignoring time and space complexity can severely impact performance. Without scalability in mind, solutions that work for small inputs may fail for larger ones. For example, summing subarrays with nested loops can result in O n squared complexity when a more efficient O n approach using prefix sums could be implemented instead. Another area to be cautious about is the incorrect updating of state variables during iteration. Variables like scores, power, or indices need to be updated consistently to avoid logical errors. To prevent this, ensure clarity in how and when you modify these variables. Debugging techniques, such as using intermediate print statements, can be invaluable for catching mistakes early and verifying that your logic aligns with expectations. In interviews, being able to identify patterns quickly can be a game changer. Many problems, including the bag of tokens, align with common patterns such as the two-pointer technique or dynamic programming. Recognizing these allows you to approach solutions systematically and save time. It's also important to explain your thought process clearly. If you can't fully solve the problem, articulate your reasoning, the edge cases you've considered, and why you're pursuing a particular method. This demonstrates your analytical skills to the interviewer. A good strategy is to start with a simple or brute force solution to show understanding, then refine it iteratively, discussing potential optimizations along the way. Finally, be mindful of constraints. If the problem has tight limits, discuss trade-offs between time and space complexity. This showcases your ability to adapt your approach to meet the problem's requirements. Several related problems can help you strengthen the skills required for tackling variations of the bag of tokens. For example, LeetCode 55, Jump Game, is a problem that explores reachability within constraints using greedy algorithms and dynamic programming. Another is LeetCode 322, Coin Change, which involves calculating the minimum number of coins for a given sum through efficient dynamic programming techniques. LeetCode 1143, Longest Common Subsequence, is another dynamic programming problem that focuses on optimizing solutions for string comparisons. Lastly, LeetCode 560, Subarray Sum equals K, demonstrates how prefix sums and hash maps can be used to efficiently solve subarray-related problems. As for alternative approaches, the two-pointer technique is particularly effective for problems involving sorted arrays, as it minimizes the need for nested loops. However, this method often requires pre-processing to sort the input, which can add overhead. Dynamic programming is another powerful strategy for problems with overlapping subproblems, as it reduces redundant calculations by storing intermediate results. The trade-off here is that it can lead to higher space complexity, which may not be suitable for all scenarios. Finally, greedy algorithms offer a straightforward and often optimal way to solve maximize or minimize problems. They focus on making the best local decision at each step with the hope that these decisions lead to a globally optimal solution. However, it's important to note that greedy approaches can fail when global optimization depends on future states or requires backtracking. Carefully evaluate whether the problem's constraints and structure align with the greedy paradigm to avoid unintended pitfalls. Thank you for following along. We explored the bag of tokens problem and discussed strategies for solving it efficiently. Remember, mastering greedy algorithms and understanding trade-offs are key takeaways here. If you enjoyed this, don't forget to like, subscribe, and stay tuned for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!